This is the first lesson on transition metal chemistry. We're going to start by looking at something called transition metal complexes. I'm going to give a simple example of a transition metal complex to start with. At the centre of a complex is always a transition metal ion. In this case, this is a Cu2+ or a copper ion. And a complex is formed when we have species called ligands that are dative covalently bonded to a transition metal ion. So in this case, I've got 6 water ligands, and the ligands is the name that we give to these species that are forming dative covalent bonds. So here we've got both electrons being provided by the oxygen in the covalent bond towards the copper 2+ ion. So there are some important ideas that we need to think about when we're looking at this. I'm just going to circle one of these and label this as a ligand. Okay, and a ligand is a species with a lone pair that is able to form a dative covalent bond to a transition metal ion. And notice here that I'm going to abbreviate transition metals always now to capital T, capital M, just saves a bit of time. So just as a reminder that we've got our lone pair and it's dative covalently bonding to the copper 2+ ion, and I can see that because I've got an arrow coming from the pair of electrons going to the transition metal ion. There is another name for a dative covalent bond, and that is a coordinate bond, which is the word that we tend to try and use when we're talking about transition metal chemistry if we can. This whole species we can describe as a complex, and we'll tend to see it surrounded by square brackets, but we'll come on to that more in a minute. There's one other important thing that we need to think about here, and that is the word coordination number. So coordination number is simply the number of dative covalent bonds in the complex. So in this case it's 1, 2, 3, 4, 5, 6. So coordination number is the number of coordinate bonds in a complex. And notice that I'm going to be using the word coordinate bond. Coordinate bond is another word for dative covalent bond. Ligand, I'm not going to write it again, but you've got the definition for a ligand up there. A complex ion is an ion able to accept at least one coordinate bond from a ligand, and then complex is going to be a transition metal ion with ligands coordinately bonded to it. So that's introduced the idea of what a transition metal complex is. There are some different types of ligands that we need to know about. The first difference between the ligands is that the ligands can be charged, always negatively charged, because they're going to be trying to form a coordinate bond with a positively charged ion. Obviously a positively charged ligand would be repelled by it. So an example of a charged ligand would be a chloride ion. They can be neutral. We've seen water as a ligand, but we can also now see ammonia as a neutral ligand. They can be unidentate, and the word dentate here refers to the number of lone pairs that is able to form coordinate bonds. In the case of water, obviously that oxygen's got has two lone pairs, but only one of them is able to form the dative covalent bond or the coordinate bond. An example of a bidentate ligand, we're going to summarise these in a minute, is this ligand, which is 1,2-diaminoethane. This obviously represents a CH2 and this represents a CH2. But the important thing here is that we've got two sets of lone pairs that are able to form coordinate bonds with a transition metal ion. Don't worry too much about these at the moment. We're going to see in future lessons lots of examples of how to draw these and how to work out complexes with them. The word dentate refers to teeth. Right, so this table summarizes all of the different ligands that you need to know about. We need to know their formula, the charge on them. This word denticity, which if I'm completely honest, I might have made up, but that refers to the amount of dative covalent bonds that can form coordinate bonds. And then we need to think about the structure. So water is obviously quite straightforward. H2O, it has no charge, it can form one dative covalent bond, and because it's a unidentate ligand, we're not that interested in the structure, but if I just draw it there with a lone pair, then you can see that we have a complete set. Ammonia we've seen again, NH3, again it's a neutral ligand, it can form one dative covalent bond, and if I just draw it out with the lone pair, it looks like that. The chloride ligand, Cl-, it has a charge of -1. It can form one dative covalent bond, and then if I draw it with its lone pair. So we now have a look at the multidentate ligands. So if you want to pause this video to copy any of that down, do. And now I'm going to move up to here. So 1,2-diaminoethane, there's a couple of ways that we can write the formula. We can write it H2N in brackets CH2 twice NH2. We could also write it, and I'm going to have to go out the box here, H2N CH2 CH2 NH2. We'll see both of these written. It's a neutral ligand, but it's got two lone pairs. So there's two ways I can draw the structure of this. You saw me draw it earlier in a skeletal formula like that, or I could draw it like this. We then come to ethane diorate. The formula is a little bit more straightforward. It's C2O4 2-, which means it's got a -2 charge. It is also a bidentate ligand, and I'll summarise that word in a minute. There's two ways we could draw this. So I've got two oxygen atoms here, both of which have a negative charge, and they've got a lone pair there. If I wanted to draw this skeletally, which we don't really do, but just so you can see it, then I could draw it like that. And again, I'm showing that it's a bidentate ligand. So in both of these cases, they are bidentate. Bi meaning two, dentate to do with teeth. It means it can form two dative covalent bonds. The literal translation will be two teeth. And again, this one is bidentate, two teeth. EDTA is quite a complex molecule. I'm not going to go into drawing the full structure of it, but we summarise the formula as EDTA4-. In future lessons, I will show you a picture of the ligand. It's got a -4 charge, and it can form 6 dative covalent bonds, or 6 coordinate bonds. So we can call this either multidentate or hexadentate. AQA seem to call it multidentate. It's better to call it hexadentate. We don't need to worry about the structure at all. The only thing that we would need to be able to do is know this information about it and use it in a formula. So I'll leave that there for a moment if you want to pause the video. Okay, so I'm going to work through 3 examples now on how we would work out the formula and charge on a complex. So Example number 1, a complex made of a copper 2+ ion with 4 ammonia ligands and 2 water ligands. So, Cu, NH3 in brackets 4 times, H2O in brackets twice, and because it's a complex, we put square brackets around it. Now the charge on this complex is a mixture of the charge on the ion and the charge on the ligands. Both of these ligands are neutral, they have no charge, and the copper has a 2+ charge. That means overall this complex has a 2+ charge. Iron 2 ion. So I've written this out rather than give us the charge. So iron, Roman numerals 2 means it's an Fe2+ ion, but I'll deal with the charge in a minute. And 4 chloride ligands. I don't have to put the chloride ligands in brackets because it's a single atom. So FeCl4. Then because it's a complex, I put square brackets around it. Then what I've got to do is work out the charge on this complex. I've got 2+ from the iron, and then we've got 4 chloride ligands. So we've got 4 times Cl minuses, which in total is a 4 minus. So that 2+ from the iron and 4 minus from the ligands means overall this complex has got a 2- charge. My final example has got a multidentate ligand in it. Now in this case a bidentate ligand. So Cu, apologies, that should be Cu2+ there. So Cu in brackets C2O4. So that's the formula for the ethane dioate ligand. And then in brackets H2O twice. Put big square brackets around the whole thing to show that it's a complex, and then let's work out the charge. So we've got Cu2+ gives us 2+. Then we've got 2 times ethane dioate ligands. Each ethane dioate ligand has a charge of 2-, which gives us 4- overall. The water ligands are not charged, so overall the 2+ and the 4- give us a 2- charge there. If you've got this sheet, you will see that the next page is an example. 10 questions for you to have a look at. Let's zoom out so that you can see all 10 of those questions. If you printed out the sheet, have a go at doing those questions now. I'll stop for a moment so you can pause the video. And if you finish that, I will put the answers up. I'm going to zoom in so the answers are a little bit clearer, so you can see the answers for questions 1 through to 6. I'll stop for a moment so you can pause the video. And then the answers for questions 7 through to 10. And I'll stop for a moment so you can pause the video. Okay, so that concludes our introductory lesson. One of the most effective things I've found when teaching this is that, and this is why I do it early in the year 2 part of the course, is there's a lot of information that you need to learn for this particular topic. In particular, the information summarised here. One of the best learning activities you can do is, as a retrieval activity, is maybe once every 2 days for the next week or so, is try to repeat this information from memory. You could also make flashcards about it and test yourself on it. As long as you're using active retrieval methods to try and learn this, that will be the best. Thank you very much.